Okay, so what if I told you that looking at more data, the big combined picture, can sometimes lead you to the exact wrong conclusion? It sounds completely backward, I know, but it happens all the time. And to see how, let's start with a really powerful real-world example.
So take a look at this. This is data from a 1991 study on murder cases in Florida. And at first glance, the trend seems pretty straightforward, right? When you lump all the cases together, Caucasian defendants got the death sentence about 11% of the time, while African American defendants got it 7.9% of the time.
So just looking at this, who seems to be getting the harsher sentence more often? The numbers point in a pretty clear direction. But I want you to hold that thought, because the big picture here, it's not the full story, not even close. That conclusion, the one that seems so obvious from the combined data, it's completely wrong. And the reason why is that we're missing a super important piece of the puzzle, a hidden variable that basically changes everything.
This crazy phenomenon actually has a name. It's called Simpson's paradox. And it's what happens when the average of all your data tells a story that is the complete opposite of the story told by the smaller individual parts. It is a statistical trap, and you'd be surprised how easy it is to fall into. Now check this out. This is the exact same data as before. We haven't changed a single case. All we did was add that hidden variable, the victim's race, and just look what happens. When the victim was Caucasian, African American defendants faced the death penalty almost 23% of the time. That's compared to just over 11% for Caucasian defendants. And when the victim was African American, the same pattern holds. In both subgroups, the trend is the complete opposite of what we saw in the overall average. The paradox is right there in plain sight. I know, it feels like some kind of statistical magic trick. How can the overall average go one way when the average in every single group goes the other? Let's use a really simple analogy to make this make sense. Okay, picture a school. Simple enough. On average, the girls have longer hair than the boys. Now a new boy joins the school. And let's say his hair is longer than the average for boys, so when you add him to the boys group, their average hair length goes up. Makes sense. But, and here's the key, his hair is still shorter than the overall school average. So when you add him to the total population, the school's overall average hair length actually goes down. The boys' average went up, but the total average went down. That's the core mechanic of the paradox. So here's the really crucial point. This is not just some weird textbook example or a statistical party trick. This paradox shows up in the real world, with really serious consequences. It pops up in everything from university admissions to life or death medical studies. Take this famous case from UC Berkeley. When they looked at their overall admission numbers, it looked like the university was biased against female applicants. But when they broke the data down by department, the story completely flipped. In most individual departments, women were actually admitted at an equal or even higher rate than men. So what was going on? The hidden variable was that women were applying in much larger numbers to the most competitive departments, like English, while men were applying to less competitive ones, like engineering, that just happened to have higher admission rates overall. This example is just brilliant because it shows you how dangerous this can be. An analysis of Navy sailors who fell overboard found something shocking. On average, you were more likely to be rescued if you weren't wearing a life jacket, which sounds insane, right? Well, the hidden variable, of course, was the weather. Sailors generally only put on life jackets during dangerously bad storms, when rescue was incredibly difficult for everybody. So when you look at each weather condition separately, good weather and bad weather, wearing a life jacket always improved your odds of survival. And this thing hides in so many different fields. It's a constant threat in medicine when you're analyzing how effective a new drug is. It's a total minefield in law and policy, as we just saw. And, in the age of big data, where we're smashing together these massive data sets from all different kinds of user groups online, the potential for these hidden paradoxes is just bigger than ever. All right, so if this paradox is lurking everywhere, how do we spot it? How do we make sure that we're actually seeing the real story in the data? Well, the good news is there's a pretty clear way to approach it. It all starts with understanding these two ways of looking at data. You've got aggregated data, that's the combined total. It gives you that 30,000-foot view, but it can hide these reversals. Then you have stratified data, where you break it down into meaningful subgroups. That's what lets you see the true relationships that are actually at play. But, modern analysis takes it a step further. It's not just about randomly splitting data into groups. It's about thinking like a detective, using something called causal reasoning. You really have to ask yourself, what's the story behind the numbers? What other factors could be influencing the outcome here? It's like knowing that bad weather causes people to wear life jackets, and it makes rescue harder.
So here's your takeaway toolkit for spotting this out in the wild. The next time you see a surprising statistic, always ask, what are the underlying subgroups here? Is there a hidden variable, some kind of confounding factor that could be driving this whole trend? And maybe most importantly, what's the logical, causal story that connects all these dots?
And that really leaves us with a final, kind of provocative question. When you see a headline or a study that makes some huge, sweeping claim based on a single average, it's worth taking a second to think. How many of the facts that we think we know are actually just a Simpson's paradox, waiting to be unraveled?